Yes, so I hope you hear me, so if there are issues, please let me know. So before starting, I should correct myself because I was asked about the block experiment, let's say the order of magnitude of number of atoms that there were in there. And actually I checked in the paper, it is of the order of 10 to the 3, so it's much more than what I said. Okay. And having said that, so we were somehow, let me take over from where we were last time. So I was going through this introduction, definition of many-body localization, and I stopped when discussing issues related to transport and dissipation. And for that, I had introduced this Kubo formula, or actually this dissipative part of conductivity given by the Kubo formula. And let me just remind the terms that you see in here. So this was a current, and these are matrix elements. So let's assume we have a finite system here. So these are matrix elements of the current operator in the basis of eigenstates of your Hamiltonian. And then there were terms which were related to the density matrix describing the state of your system in absence of the field, so the perturbation. And there was this term in here, which contains the dependence on the energies of the eigenfunctions themselves. And I was stressing what was the role of the regulator. So this was, at the beginning, I introduced this eta just to make my integrals converging. And this gave rise to these contributions, which are of the following form. So now let me take zero frequency, and the idea is that these quantities in here were essentially Lorentzians with a little bit of dispersion, which is given by this very weak regulator eta. And the Lorentzians are centered in E alpha minus E beta, which is the energy difference between the eigenfunctions appearing in this sum. And the point in here was, so I stopped by stressing that there were several limits involved in this formulation here, and that somehow it is important, if you really want to compute contributions to dissipative transport, to consider the fact that you have to take the thermodynamic limit before sending this regulator to zero. And this allows to give an interpretation to this in terms of symmetry breaking, if you want. So the idea is that this eta plays the role of some infinitesimal dissipation that you put in your system, which breaks unitarity of your dynamics. So we can interpret it as, if you want, coupling the system to an infinitesimal bath. Then we take the thermodynamic limit, and then we send this infinitesimal bath to zero. And the question is whether the system is able to self-sustain transport and dissipation even after we have sent this infinitesimal coupling to zero. And therefore, we can interpret this eta as, in the same way as we interpret symmetry breaking field, for example, in an Ising-like transition. And the symmetry in here is not something which appears in your partition function, but you can think of it as something which matters in your dynamics, so it would correspond to time reversal. And so the idea is that when you are localized, in some sense, you are not breaking this time reversal symmetry, even if you take systems which are thermodynamically large. Okay, so going back, or insisting a bit on this order of limits, I also wanted to stress something else. So there is another limit that we are taking in here, in the sense that we are working in a framework which is linear response. And linear response implies that we first assume that the field is small, so the absolute value of my perturbation or the modulus is going to zero, and this is taken before sending the frequency to zero, which gives our DC response for the conductivity. And given the lectures of this morning, I wanted to stress that this is different from what you do when you look at adiabatic limits, where you typically take this frequency going to zero before. And actually, if you do this in these localized systems, you find the differences. So with adiabatic perturbation, you can actually induce a little bit of transport in your system, because you can induce Landau-Zener transition between states which are localized far away in space. And if you want to look at this other limit and connections to transport, there is a reference in the supplementary file where this is discussed. Okay, so some other comments on this Kubo formula. So somehow this will perhaps become a little bit more clear in the following, but the idea is that when you have these many-body localized systems, the reason why you have this quantity at zero frequency goes to zero is because you basically have a competition between these two terms. So between the matrix element and this term, which depends on energy differences. And the competition, you can interpret it in the way I wrote up in there. So you somehow see that your many-body eigenstates are such that if you take two eigenstates which are very close in energy, so such that the energy difference is small, and in that case, this contribution in here would be large, what you typically find is that for those pair of eigenstates, the matrix elements of local operators are actually small. And this corresponds to the fact that eigenstates which are very close in energy, if you look at them locally, they are actually pretty different. So they are locally distinguishable one from each other if you probe them with local operators. And this will be connected to the discussion on Eigenstate thermalization hypothesis that I will introduce in a minute. You hear me like that? Okay. Okay. So we'll come back to that when discussing connections to thermalization. And to conclude this about transport, I also wanted to stress that these type of statements on the fact that your dissipative part of the conductivity vanishes, if you consider Anderson systems, so the single particle case, they are actually proven mathematically. So in that case, if you put yourself in the regime in which the disorder is sufficiently strong, you can, people proved that conductivity vanishes. And this is what mathematicians called dynamical localization, and they use this terminology to distinguish this type of statement from other statements that have to do with the nature of the spectrum of your Hamiltonian, which they call spectral localization, and which we will discuss in the following lecture. Okay, so that concludes somehow the part about transport. And just to finish with discussing the definition that I gave at the beginning, there was another point which had to do with not dissipation, but with dephasing in some sense. And this connects with a comment that was raised the other time about the fact that when looking at this imbalance experiment, it looks as if what you're probing there is actually single particle localization. So you wonder what is the effect of interaction? Am I measuring something which is truly many-body or not? And in fact, in many cases, people tend to consider the statement of many-body localization as the fact that you have localization, and this phenomenology is stable with respect to adding weak interactions to your system. So this is one way to see this, but I wanted to stress that, in fact, interactions matter when you look at your system, and they show up explicitly in the dynamics. And what you can look at to see this in a rather clear way is, for example, the dynamics of entanglement. After a quench. So you go back to this dynamical framework of doing quantum quenches, and this time you may think that you start from an initial state which has zero entanglement. So you can take, if you have a spin chain or a one-dimensional lattice with fermion, you can initialize your system into a state which is a product state. So let's say a random product state of the form E1 plus B1. So this will be the state of the first spin, and it is a superposition of up and down, and then you take something similar for the second spin with maybe different coefficients. and so on and so forth. Okay, and then you let the state evolve with your fully interacting Hamiltonian. And you measure entanglement by looking, for example, at the so-called bipartite entanglement, which was already introduced. So if you have a chain, what you can do is you split it in two parts, like here, and you focus only on one half of the system. So you introduce a reduced density matrix, rho 1 of T, which is defined by tracing over the second half of the system your full density matrix. And then you look at the so-called half-chain entanglement entropy that you define as minus trace of your reduced density matrix times the log. Okay. Now, the idea is that this quantity starts from 0, but then under time evolution, you start, in general, you develop some quantum correlations between the two subsystems, and entanglement entropy will grow. But the way it grows in time is rather different, depending on what is the system that you are considering. So I had plots of numerics in the slides, and you can check them, but now let me just draw roughly what you find by simulating time evolution of your system. So if you consider a generic system, which is not, well, okay, let me not draw the transients. But if you have a generic system which is not MBL, and you can think about clean systems, but also integrable systems in this particular case, what you find is that this entanglement actually grows pretty fast in the sense that it grows linearly with time. And if you have integrable system, you understand this, you have quasi-particle pictures, and you know that you have a light cone that determines the fact that there is some velocity through which this information is propagating. But this scaling is true also in general for systems which are clean but not integrable. Whereas if you look at the non-interacting limit of disordered Hamiltonian, so at the Anderson model, what you find is that your entanglement remains small, so you have a little bit of a transient where it grows a little bit over time, but then it will eventually saturate to some value that I call C or little s, which is something that does not grow with the size of your system. Now, what happens in MBL is that your behavior is a bit in between these two. So you still have a transient, and then you have a growth in time, which is still unbounded, but which is quite slow in the sense that it goes only logarithmically in time. And I would say that this, so first of all, why do you have such a logarithmic growth? Well, this emerges because as soon as you put interactions, you have dephasing mechanism in your system, and these are such that essentially the degrees of freedom that you have in your region 1 of the system eventually will start talking or will start interacting and dephasing with the degrees of freedom which are arbitrarily far away in the second half of the system, and this shows up in this unbounded growth of entanglement. But you see that this is much slower. And I would say that this is one of the hallmark of this many-body localized phase. So first of all, it's something which allows you to sharply distinguish this between, or with respect to the non-interacting limit. And it is, together with the suppression of dissipation, somehow the characteristic feature that you can check when you look at time evolution of these systems. So combining these two observations, we can understand what I wrote at the end of the definition, which is the fact that in MBL, you can understand these dynamics as being characterized by the fact that you have dephasing, but you have no dissipation. Okay. Okay. Okay, so with this, I think we are done with what I defined as question 1, which was devoted to understanding what one means when speaking about out of equilibrium for these disordered systems. And now I wanted to go to somehow the second question, which is a bit a parenthesis, but since I think perhaps my terminology yesterday was not clear to everybody, I want to spend a little bit of... Yes, I will come to that. It has to do with integrability and the structure of the Hamiltonian once you write it in terms of your conserved quantities. So that will come in the next hour. Okay, so question 2 was more about, so I say that this is out of equilibrium, but then we are in a framework of a unitary evolution, so one should somehow ask what would equilibration mean in this setting. And let me write what would thermal equilibrium mean. And just to recap a little bit the observation made yesterday, so why is this a question which is not totally stupid? Well, because as we said, your dynamics is unitary, so you may make a guess, which is of course wrong, about what would equilibration mean, and that guess would be that you start from some density matrix, which is time evolving, and in some long time limit, you want this to somehow converge to something which is Boltzmann-like, so which looks like this. And we know that, of course, this cannot happen globally in your system because your dynamics is unitary, so you are starting from a pure state, and you will stay forever in a pure state. There is no way that you can converge in any long time limit to something which is a mixture, like your Boltzmann measure in here, so such that the trace of rho square would not be equal to 1, for example. And also you know that this cannot be true because your dynamics preserves information on the initial conditions, so how can it be? So we have to be able, by applying, let's say, the inverse unitary for any time evolved state, we have to be able to go back uniquely to our initial conditions. So how can it be that you converge to something that doesn't know anything about your initial condition except for this constant beta, which just depends on the energy of the initial condition? So of course this does not happen, and you should make you should ask something weaker to your system. And the key, as I think is clear by now, is that you should ask, where is this information of our initial condition, where is it encoded at much later time? So it is there, but which type of operator encode it? And this obviously leads to introducing this idea of locality and looking only at your system locally and not globally. So now I'd like to give a few definitions of what I have in mind, and this definition you will see are only necessary conditions for thermalization or equilibration, but they are enough for me because we will see that they are already violated when you think about MBL. So this has to do with relaxation or thermalization of finite subsystems when the size of your system goes to infinity. So what I have in mind is that I have my whole system which is closed, isolated from everything else. So this has a typical size, which I call L. And then I look at some finite subsystem. So if you have a lattice, this means that I want to look at a finite bunch of sites and only on the degrees of freedom which are in this subsystem. So there will be a typical length of the subsystem, which I call little L. And I want to define some convergence that should hold for arbitrary finite subsystem S for arbitrary observable that I call A, so arbitrary operators which are supported on the subsystem. So this is, you think it as spin chains, so this will be Pauli matrices which act only on the sites that belong to this subsystem. And also I want to make statements that hold for somehow arbitrary initial condition within some class. And so no, okay. And so let me focus on initial conditions that are somehow associated to a well-defined value of energy, so which do not have too large fluctuations of my conserved quantities. So let me remind that we are specifically considering a dynamics with an Hamiltonian that is time independent, so which is conserving energy. And on the initial condition, I can ask, for example, that the fluctuations of this energy, so I hope I can squeeze it. Okay, maybe I'll write it here. So I want that if I compute the trace of my energy density square on the density matrix at time 0, and then I subtract the square of the energy density itself. So these are the fluctuations in energy. I want that when I send the system size to infinity, this goes to 0. So I'm asking that I have sub-extensive fluctuations of the energy. And this is because I want to define a well-defined temperature for my associated to the initial state. So if I start from an initial condition that is, for example, a linear combination of states which are macroscopically different and which correspond to very different energies, perhaps it would be too much to ask what I'm going to ask about thermalization. So you can think about initial conditions that are physical in the sense that they have some product-like structure and they will naturally satisfy this, and actually this difference will decay as 1 over square root of the volume, as it usually happens in a thermodynamic setting. So in this case, what I would define as a relaxation, and I think that several people here would actually call it equilibration, is the following. I take my arbitrary operator. I take the expectation value with respect to the time evolving state. And then what I want is that in the limits, so in the limit of time being large and then also system size going to infinity, this expectation value converges to something which is stationary, so time independent. Let me call it A infinity. And if this is true, this stationary value has to coincide with the time average of this object in here. So this is also limit t going to infinity of 1 over t time average. And as I said, so I think that in the quantum literature, you often find this as being defined as equilibration, and there were some comments yesterday about this. So the reason why I use the term relaxation is that typically, so here you are looking only at one-point functions, so operators and not correlations between operators at different times. And for example, if you talk to classical people doing glasses, and if you speak about equilibration, they would not think about stationarity alone, but they would also think about fluctuation-dissipation relationships and correlation and response relationships, and those usually involve a well-defined notion of temperature that allows you to map correlations and response. So there, the notion of equilibration is, I think, a little bit stronger than what I'm writing in here. But okay. And then, of course, thermalization or thermal equilibrium. Then corresponds to the statement that this time averaging here actually coincides with what this Boltzmann-Gibbs measure would give you, that yesterday I called expectation value over this Boltzmann-like density matrix of the same operator A, with, again, the temperature that is fixed by the energy of the initial condition. And so you see that you're probing this only locally, so you, of course, do not expect that the full state of your system, the full density matrix, converges to this. So the density matrix will evolve into something which is very complicated, but if you probe this locally by means of these local operators, then it looks as if the system is thermal locally, and it is thermal with a well-defined temperature. Okay, so why did I say that this is only a necessary condition? Well, the reason is that when you define statement like this, of course, you have to specify several things. So the initial condition, the type of dynamics, but you also have to specify the type of observables for which you ask this convergence to happen. So these are remarks. And in general, so if you do this type of reasoning beyond MBL, the class of observables for which you ask such a convergence to occur is a bit larger. So in here, I'm looking at what I would call strictly local observables, which are really supported on a finite number of sites. So for example, the density at one particular site would be an observable which belongs to this class. But in general, when you think about clean systems and other type of systems, you want to generalize these definitions to observables which are local. And these can be linear combinations of these strictly local observables. So for example, let's take the occupation number in momentum space, which is a sum over all your sites of e to the k a, and then you have the density the site A. And of course, you don't ask this for non-local operators. And one example of this would be, in general, let's say a projector onto an eigenstate of your Hamiltonian. This is typically non-local. So if you look at my definition with these finite subsystems, you know that this is already violated by MBL, and this is what we discussed last time. So we looked at a density operator at a single time, and we saw that this was not converging to the right thermal expectation value. But based on my definition, if you take, for example, free fermions without potential, you would see, you would see that locally in space, they would fulfill that definition. So you have to enlarge the class of your observable to see that actually also in that case you're not thermalizing because your momenta are conserved. So that is a special case of integrable systems. And your momenta are local operators in this sense, but they are not local in the sense that I'm considering in here. So so if you want to define thermalization in general, you would want it to hold also for observables which are linear combination of observables which are really local in the sense that they act on one particular site of your system, such as momentum operator, occupation numbers in momentum space. So that you would call a local operator. And in general, when you think about thermalization, you want that to thermalize as well. But that would not fit into my class of operators there, which are supported only on a finite number of sites. No, I mean, I want to stop here, of course. So the idea is that you need a reduction of information. So you cannot expect these conversions to hold for arbitrary operators. In particular, you don't want to include operators which probe an exponentially large number of coefficients that Yes, so I think that, I mean, to really measure a projector into an eigenstate, what you need is you have to distinguish this particular eigenstate to all the other eigenstates, so you need 2 to the L quantities to fix. And this is a lot. Whereas if you look at this class of observables which are measurable, it is only order L information that you are probing in here. So there is a reduction of information in going from here to here. You mean if my eigenstate is such that my system is decoupled, then it is, of course. But I mean, in generic situations, your eigenstate would not fit into this. No, okay, you're right. It's. For free systems, yes. Yes, but in that case, it is this which is special. For systems which are not free but interacting, typically, I mean, this is much more complex and non-measurable with respect to this, which are real observables in the sense that you can measure them. No, but I agree. For free fermions, it would be free systems in general is a bit a special case. Okay. But let's say for me, it is enough to focus on this. And by looking only at this type of observables, I can already claim that, that I am not thermalizing. And so maybe okay, let me add a second remark. Yes, so it's a bit similar, yes. So the question is, if we have an MBL eigenstate which is localized in space, would you still consider the projector as non-local? Okay, no, so in that's the point. So in that case, we will see that we will be able to identify so that there are conservation quantities in systems which are MBL, and these conserved quantities have a local structure. And so we can map our eigenstate one-to-one with a set of occupation numbers or of quantum numbers of these local conserved quantities. And so in that case, I think by specifying a number which is only extensive of this occupation number, you can identify which eigenstate you're looking at. But I stress that this is really special of either free systems or localized systems. So in general, there is no hope that a projector like this is something that you can measure for a realistic system in an experiment. So you would need to specify really 2 to the L coefficients to pin down and identify precisely this eigenstate. Okay, I hope that's clear. Okay. Okay, so the second comment I wanted to make is about this idea that you have to take okay. Why you have to take L going to infinity, or what happens for finite L. So for finite L, we know that actually you cannot have such a convergence to a stationary value because you have these quantum revivals. So one way to see this is that you take your expectation value you compute it with the Lemon representation into a basis of eigenstates of your Hamiltonian. So you will have terms which are diagonal in this basis. So this is your density matrix at time 0, and then you have diagonal matrix elements of the operator A, and then you have the off-diagonal terms with the phase. And eigenstate A being different from eigenstate B. And now here you have a finite sum over a number of oscillating terms. So you know that if you, for example, take the average with respect to time of this quantity, this will not change, but this will be typically killed by the time average. So let me call this the expectation value of A time averaged. And let me call what remains delta A of t. And the comment of yesterday is that, strictly speaking, this expectation value in a finite system is a function which is quasi-periodic in time. Which means that if you wait long enough, you will see that your expectation comes back arbitrarily close to the value that you had at time t equal to 0. So if I plot time versus this quantity square, so I start from an initial condition which is out of equilibrium for my local observable, so these fluctuations will be large, and then the time evolution will typically bring me close to the average, but then at certain times I will have out of equilibrium excursions, and then I will have these revivals where I get very close to the value that I had in the initial condition. And the timescales over which you have these revivals, of course, depend on the spectrum of your system. So these are times such that all of these phases become multiples of 2 pi, so you get a factor of 1. But you can argue that typically they go as the inverse of the gap in the spectrum, so they will go exponentially with the size of your system. And so this is why I was asking size of the system going to infinity, so you, in some sense, want to push these timescales away from your observation window, so you take L going to infinity before looking at the long time limit, and then you can hope that your observable reaches a stationary value. And the way you interpret this physically is in terms of dephasing. So in that case, this sum will become a sum over infinite frequencies, and you argue that these frequencies are only incommensurate. So you sum over all of these, and this effectively averages to 0 when you have an infinite number of contributions in this sum. And you can make this more mathematically stable as a statement. You use Riemann-Lebesgue lemmas or things like this. But let's say the idea is that in this limit, you typically have dephasing mechanisms that give you stationarity. But if you want to probe this at finite L, then from here you see that there is another thing that you can do, which is to time average directly and kill this term, even at finite L, by means of the time average, and see what happens to your diagonal term, whether it is indeed thermal or not. And this corresponds to so-called relaxation or equilibration or thermalization on average. So the idea is that you ask that these fluctuations square when you time average them, they remain smaller than a given threshold. So that your dynamics is such that it keeps you close to the average for most of the times, so that when you average, these excursions to out of equilibrium do not contribute to the average. So the reason why I'm introducing this is that this now leads to something that one needs to discuss when looking at MBL, which is so-called Eigenstate thermalization hypothesis. Because this statement of thermalization on average is essentially guaranteed. So this is point 3. Is implied by ETH, which stands for Eigenstate thermalization hypothesis, which is an hypothesis that you make on the structure of the eigenstates of your Hamiltonian projected on the operator, so on the matrix elements. And the hypothesis is as follows. So you first, you also have to ask something when you think about dynamics about the initial state, and you ask something which is very similar to what I wrote about fluctuations of the energy to be bounded. So you ask that your initial time density matrix essentially is contributed only by, so it has a significantly large matrix element only on eigenstates which correspond to a precise energy shell. So this is large for only for those eigenstates such that the corresponding eigenvalue is in some energy window where the energy itself can be extensive, but this delta E is sub-extensive, so it goes like L to some power which is smaller than 1. And then what you ask is that your matrix element have a given structure. So for your local operators, AIB, so for the diagonal term, if you want thermalization on average to occur, you want that this diagonal term reproduces the thermal expectation value of the operator itself. And then for the off-diagonal term, you basically that this is exponentially small in your system size. So, the Zrednicki formulation of ETH goes like this. So it is an ansatz. And what you ask is that here you have a factor. OK, I will write it down and then I will comment. So you have two eigenstates. So what you can do is you define the average between these corresponding energies, and you define the difference. And in your off-diagonal term, what you're putting in here is a factor of e to the entropy. So this is basically related to the square root of the number of states that you have in this energy shell around the average value. So the entropy in here is extensive. I'm considering 1D systems in here, so it will go with the size of your chain. And then you have some spectral function, so some function which you assume to be smooth in these energies on which it depends. And then you have something which fluctuates because you can change the eigenfunctions that you're looking at within this shell. And this is something that in your ansatz you typically model with as a random variable. And since originally this was somehow motivated by quantization of classical systems which are chaotic, so this is related also to Barry conjecture, so the idea was to assume that this fluctuating number here have a distribution which is Gaussian.
Yes, sorry. What is the point of this prefactor root f? Why don't you include it in the
No, I just want to say that you will have some dependence on the energies that you are looking at.
Because R alpha beta is independent of E. Is that?
Yes. So this is something of order 1 on which you factor out the dependence on the energies, and then you code it into something which you assume to be smooth at the scale of the energies that you're looking at.
Okay. And why do you put a square root?
No, okay, so okay, let me just.
What? No, but I guess it's because the square is going to appear somewhere, so what?
No, I think you assume some sort of average of terms which you treat as independent. But that's not important. I just want to say that here you have a function. But the important, let's say, thing that you need for time evolution is that the off-diagonal matrix elements are suppressed exponentially in the size of your system. So, okay, let me say something. So you have two things in here, and all the interesting thing about how you converge to equilibrium come from the structure that you put in here. So this will give you information about the dynamics. But then the fact that these are suppressed, let's say, extensively because you have this entropy factor is what guarantees that eventually if you take these averages, the stationary value will not be contributed by this. And then you can only focus on this diagonal. And to have thermalization, you have to impose a constraint only on this being equal to the thermal expectation value that you want. But now there's a lot. No, I just wrote erratic in the sense that this is something that in your system will fluctuate, and you want to model it with a random variable with some statistics that you want to characterize. So the statistics of this random variable actually depend on the system. Well, first of all, this is an hypothesis, so it's not something that you prove on your system. You assume an ansatz like this, and then you show that if this ansatz holds, then your system thermalizes according to this definition. But now I would say there is a lot of research active in these days in trying to characterize these terms and to see what the shape of these ansatz implies for the dynamics of your system. So for example, originally which was thought of motivated by this extension from classical to quantum chaotic system with these variables having a Gaussian distribution. But if you look at random systems in the delocalized phase, so where you know that you thermalize, actually in that case you see the effect of the presence of your randomness in the fact that you have an anomalous statistics of these quantities which are non-Gaussian anymore. You have some tails and so on and so forth. So really the dynamics depends on what you assume on this term, but for the purpose of what I want to discuss in here, which is just convergence to a stationary value which is thermal, I will always only use the fact that this is suppressed and this guarantees my convergence, and then I will focus on checking whether this is true or not in my system. Is this clear? Okay. Okay. And so the reason why I wanted to speak about ETH is that when you do numerics on these random systems, actually this is what you look at typically. And so now I will show you plots about this. Oops. But first, okay, the comment is that in MBL, so with the terminology that I said, you have relaxation, but you have no thermalization. Okay, so now let me maybe show you some of these plots. And let me go back to the comment that I made before, that in this system you have this, when I was writing down the expression for the conductivity, I stressed that you have competition between energy differences and matrix element, and that if you look at eigenstates in this MBL phase, if you look at states which are very close in energy, so which would fall into this energy window, and you probe them locally, so you look at finite region of space, actually they look pretty different from each other, and you can distinguish them by probing local operators. And this is, of course, not compatible with the statement that you're making in here. So with this statement here, what you're saying is that all the eigenstates which are very close in this energy shell, if you look at them only probing these local operators, they look all the same. So they all give rise to diagonal matrix elements which are the same, which just depend on beta and not on the particular eigenstate that you're looking at. Which is true in generic systems, but it is not true in MBL. And here you see some examples of the numerics. So this is one of the early numerical results of Hughes and Pal. So what they are looking at is this XXZ chain that you see, where your randomness is in these fields HI. So the strength of the disorder is now, I choose the other couplings equal to 1. So what I call H in here is what I call delta so far. And what they look at is this, let's say, expectation value of my local sigma z operator at a given site on an eigenstate n, labeled by n. And alpha here labels the particular realization of disorder. And the different curves in here, so the different colors, correspond to different strength of the disorder. So the blue one is a weak disorder, and then the pink or violet one is the strongest disorder. And what you're plotting as a function of system size is the difference in this local expectation value between two eigenstates which are adjacent in the spectrum, okay? So if you add ETH, what you would expect is that this difference is 0 when you send the size of the system to infinity, or you make it sufficiently large. And this is more or less what you see at weak disorder. So you see that this difference decays, so there is a log in there. Whereas, as you see, if you take the disorder strong enough, it looks as if such a difference remains of order 1. So by probing sigma z on one eigenstate and on the next one, I see two different values which are separated by order 1, which are different by order 1. And this remains true all over the, let's say, system size that they have access to with these numerics. So this is precisely what I said so far. So you look at this energy shell, and two eigenstates which are nearby, they are actually different in the expectation value of this local operator sigma. Yes, maybe I just show. So this tells you that ETH does not hold true in here. But still, as we saw, we have, you have relaxation because you have dephasing in your system, because you have interaction, which means that actually during the time evolution, your expectation value will converge to some value that is time independent, and they will converge as a power law, and this you can also explain using what I will discuss in the next hour. But the stationary value that you reach is not the one that you would expect based on thermodynamics. Okay, I think we can pause here.
Any questions? There is a question.
Yeah, sometimes when people want to check ETH numerically, they plot these these clouds of points. So you just plot expectation value of your local observable as a function of energy, and then you just plot the value that you find for all eigenstates.
To show that it
yes, and then as a function of system size, you see that the cloud shrinks and eventually falls onto a line. I mean, you see what kind of drawings I'm talking about?
Yes, so you're asking if...
Yeah, what happens if you do that here?
So, okay, so this cloud, so there are two information in that. So one is on the fact that somehow the off-diagonal terms are small with respect to the diagonal one. And this is, I think, okay. The other one is that all the state in the spectrum, if you just look at the diagonal, converge to the same value. So they concentrate on the same value. And this would not be true in here. So if you look at the sigma, okay, let me maybe just give an intuition of why. Why this happens? Well, this happens because, as I will say in a minute or after the break, the idea is that your eigenstate En is some sort of weak deformation of the eigenstate of the sigma z operators. So if you just have an eigenstate, an Hamiltonian which is diagonal in sigma z, then of course your diagonal matrix element eigenstate by eigenstate will fluctuate of order 1. So you have -1 + 1, -1 + 1. And something similar you expect in this situation in here, because your eigenstate is not an exact eigenstate of the sigma z, but it is an eigenstate of conserved quantities which are weak deformation of the sigma z. So state by state, you have plus and -1. Of course, if you average overall the state, you don't see these fluctuations, and this is why thermodynamics doesn't tell you information about the fact that you are MBL, and this is purely dynamical. So thermodynamics is averaging over all these eigenstates, and this averaging is an average over plus and -1, and it will give you 1/2, and so it would look as if the state is thermal. So by looking at your partition function or thermal average, you don't see this. Okay.
Other questions?
I think that all these statements about the relaxation, they strongly depend on the operator that you look at. I mean, here you take sigma z, so it's quite obvious that if there are no interaction, it will not relax because the state that you built are eigenstate of sigma z. But
well, okay, here they are not. You have interactions, of course.
yeah, I mean, but I want to say that if you measure some other observable like sigma x.
Yes, this is what you have here.
That's a z, no? There.
One is z and the other one is x.
Okay, so.
And you still have, let's say, power law. Now, the value at which you converge, of course, is different. In one case is order 1, in the other case is 0.
Yes, but if there are no interaction, what happens to sigma x?
No, if there are no interactions and you have, so
imagine that you switch off that term, the J1.
which one do you want to?
J
I mean,
transverse.
of course, if you just have sigma z and you look at sigma x.
Yes, it will go to 0.
Exactly.
And so what? I don't understand which is the difference then.
No, that.
Why you say that interaction are important to relax? I think it's important to the observable at which you look at.
Absolutely, but you have a statement on the fact that, okay, there are several things in here. So first of all, the way you relax is not is power law, which is something that you don't find typically in systems which relax much faster. And then the value that you relax to, of course, if you choose sigma z and your disorder is in the sigma x basis, you don't see in the sigma z. If you choose sigma x and your disorder is in the sigma z basis, you don't see, by looking at the stationary value, it's the same that you would have without disorder, so it's 0. But if you look at operators in a basis which have a huge overlap with your conserved quantities, which is the one selected by the disorder, then you do see a difference. So in one case, you would relax to 0 if you add some interactions. In the other case, you stay finite and away from 0.
Other questions?
But of course, the statements here are for all observables. So you have, if you find one class of observables for which the stationary convergence is not the thermal one, then you can claim that you do not thermalize. And here, the class of observable is selected by the term where you put the disorder, so it would be sigma z, sigma z in here, yes.
If no other question, because it is a bit late, we reconvene in 5 minutes at 3:10. So let us start again for the second lecture of today.
Okay.
Can I ask a question?
Sure.
It is related to the Berry conjecture that you briefly mentioned before. I was wondering, for explaining ETH, we usually look at the fact that there is some randomness, or at least that we can fit the properties of eigenstate of the energy spectrum of interacting models by random models. And this is a crucial property, as far as I understand correctly, to define ETH. And this is for clean systems, non-integrable systems. I was wondering, since ETH is not valid in MBL systems, is the randomness property that you fit inside the Hamiltonian that breaks down this randomness property of the high energy spectrum, or is something different? I don't know if the question is.
Yes, it is. I hope I heard properly, but it is. So the idea is that if you have a strong disorder in such a way that you will have a class of operator which couple to your disorder field in the Hamiltonian, and the disorder, when it is strong, it selects this class of operators as being, in some sense, a special basis. And this is why you break this randomness that you're referring to. And you see this in, if you want to think about more observables which are perhaps more natural, if you are thinking about chaos and random matrices, you see it, for example, in level statistics. That is not the Wigner-Dyson one that you expect in general when you have this type of chaotic description, but it is in here Poisson level statistics. But yes, so if the question is this generated by the fact that you have a randomness in here, the answer is yes.
Yeah, exactly what I was wondering. Thank you.
Yes. And now I will now just sketch why this is the case. So this will be very sketchy, and I think tomorrow when doing the actual calculation, this will be more clear. But somehow what you can ask is precisely what is the mechanism? So why is disorder, or how actually? So what is the mechanism which is produced by disorder in here? And as you will see, the mechanism that I'm referring to, so again, this will be, I think, clearer tomorrow, but it is what I will call suppression of resonances. And just to understand what I mean, let me start by drawing something that I think one would naturally draw when thinking about symmetry breaking, for example, or non-ergodicity in general. And this is something like this. So suppose that you have, well, you can think of this as being some effective potential in a field theory, but also you can think of this as being a single degree of freedom which evolves in such a potential. And the idea is that, as you see, this is non-monotonic, so you have a global minimum that you would like to interpret as your equilibrium state, and you have a minimum which is at higher values of the potential that you would like to interpret as your metastable state. And this is, for the moment, is classical, and let's say that we consider a dynamics which is similar to the one we are thinking of in the quantum case, so just Hamiltonian dynamics. And you know that here you would also have classically some ergodicity breaking, so if you start from an initial condition which has a low energy and which is in the vicinity of this minimum, and you just do gradient descent and follow the Hamiltonian to lower values of the potential, you will essentially converge to this metastable state in here, and you will not be able to go to the equilibrium state, which is at smaller values of the potential. Okay. Now, if you and this is, of course, because your energy is not large enough to allow you to overcome this potential barrier. So what you can do is to add some stochasticity, so you couple to a bath, you have a little bit of noise coming from the bath, which, if it is strong enough, will allow you to make these jumps. But these are processes which are very slow and very rare, and essentially the mechanism that you have in here is what gives you ergodicity breaking and slow dynamics in classical glassy systems. So in that case, your landscape is typically much more complicated. You have many metastable states, but the basic idea is precisely this. So now one question that you can ask is, what happens if you add quantum fluctuations to this system? And in general, you may expect that quantum fluctuations help you because you can tunnel across your barrier, and therefore this may help you restoring ergodicity in this situation. So this is true, but not always. So what you can do is you take this system and you write down a super simple toy model. So let's assume that you compute semi-classically, for example, what is the tunneling amplitude to go from here to here, and you encode it into some constant J. And then I decide that this value of my potential, I call it E1. The metastable energy, I call it E2. And I write down a toy model, which is just a two-level system. So I identify each of the two wells with a state. So my configurations, if this is phi 1 and this is phi 2, I write down a simple 2 by 2 Hamiltonian. So phi 1 and phi 2 becomes my states 1 and 2. And then my Hamiltonian would just be E1, J, J, E2, which is very simple, so I can easily diagonalize my dynamics for arbitrary initial conditions. Now, I'm not going to do this, so you can do this. It's one of the exercises, but what I want to stress is that, let's say, the situation is qualitatively depending on the ratio or the relationship between two energy scales that you have in here. So the first is the hopping, and the second one is the difference in energy between the terms that you have along the diagonal. And the right question that you have to ask to understand what's going on is whether there is a resonance or not in your system. Which means that your tunneling is comparable, so it's able to compete with this energy difference, so it is larger or of the order of this energy difference. And now here you can have, of course, two different answers. So if there is no resonance and your tunneling is much smaller than this energy difference, then what you find diagonalizing your system is that, of course, the eigenstate of the 2 by 2 Hamiltonian are weak deformations of these local eigenstates because J is small. So if I draw them, these are my two sides. I will find one eigenstate which will look more or less like this, and the other one which will look more or less like this. So this is psi 1 and this is psi 2. The energy differences between the energy of the two eigenfunctions will be more or less like the unperturbed one plus corrections. And of course, in this regime, I can work out things working in perturbation theory around this purely local basis. So I can develop a perturbation theory in J over delta epsilon, and this perturbation theory will converge. And will tell me that indeed the solution to the false system, I can think of it as being a weak deformation of the one that I have when J is equal to 0. And this is, in this naive example of only two sides, this is what I would interpret as localization. Because now if you think about dynamics, so let's assume that, as usual, we start from an initial condition which is where I know where is my particle. So let's say that I start with my particle in the position number 1. Then this initial condition will have a large overlap essentially only with this particular wave function. The overlap with this one will be small. So under time evolution, both contribution will get a phase, but let's say the amplitude will remain large only when projected on this particular wave function. So if I make a measurement at later time, I have a much larger probability to still find my particle in the site 1 rather than in the site 2, of course. Okay, in the other case, this is not true any longer. So if my J becomes of the order or larger than this energy difference, then my eigenstates will look very different, and I have hybridization between these local degrees of freedom. So I will get typically one eigenstate which looks like this, and the other one which is of this form. So they have a comparable amplitude on both sides. The energy difference between these is now of the order of this coupling, J, which becomes dominant. And obviously, if I try to do any perturbation theory in J over delta epsilon, so around my local basis, this will diverge. And this is telling me that what I have to do is to hybridize these 2 degrees of freedom. And in dynamical terms, this means that you are delocalized in the sense that you start with your particle at site 1, but then very rapidly, so the local eigenstate in position, so the eigenstate of position corresponding to the site 1 will have an overlap with both of these. So you admix them during time evolution, and after a while, you will have more or less an equal probability to find your particle in either site 1 or site 2 of your system. Okay, so this is for a fixed, let's say, choice of my parameter. And now what happens when you think about these disorder systems is that you put yourself in a situation in which these variables along the diagonal are independent, identically distributed. So you extract them from a given distribution, P of E, which has a typical width. So let me take a box distribution, and let me call this delta. And what you can say is that, well, if you choose, so first of all, if you extract these quantities, so now A, it's either A1 and A2. So if you extract them independently from this distribution, what you will find typically, so for most of the cases, is that your energy difference is precisely of the order of the width of your distribution. So it goes like this parameter delta. And therefore, if you choose this order strong enough, so if delta is much larger than J, you are typically non-resonant. And therefore, your system remains localized. Now, this is just 2 sides, so this is, of course, very simple. And actually, when you think about the Anderson model, the issue is not that simple. And the reason is that there you have an infinite lattice. And when you have an infinite lattice, this means that you are sampling your distribution of the random potential infinitely many times. And so you cannot rely on the fact that typically if you select just 2 sites, you have a large energy scale between them, and this saves you from having resonances. No, you have to really be careful about the distribution of your potential in an infinite size, because there you are somehow probing all of this of the distribution of your local field, and so you will likely have realization in which resonances appear. So just to be more precise, let me try to sketch this with a figure. So the observation that you can make is that, of course, in an infinite lattice, you will always find 2 or 3 neighboring sites where it happens that the energy differences in there, so between the local degrees of freedom, do not satisfy this condition, and actually they are much smaller than the local hopping J between those degrees of freedom. But as soon as this is local in space, you don't really care, because when you think about localization, you think about transport at large scales. So if you have to do a little bit of hybridization locally, this is not so important at the level of of transport at large distances. But there are other things that you may worry about, which is what I tried to sketch in here. So the idea is that, let's assume that you consider one particular site. So the red dots now are values of my random potential. And I am at a particular site 1, and I have a given value epsilon 1. And then I know that with probability 1, if I have an infinite lattice, I can choose an arbitrary small parameter delta. And I can ask whether I can find in the lattice sites such that the local potential in there is as close as epsilon 1 as I want, so such that the energy difference is equal to delta or smaller than delta. And I know that I will find with probability 1 such a site, because I'm sampling my distribution infinitely many times. The distribution is continuous, so I will always find values which are arbitrarily close to each other. Now, the point is that since your random potential is independent, in order to find such a site, if I ask for delta which is smaller and smaller, I typically have to go to larger and larger distances. And when I ask about what is the effective tunneling between now these two sites with a very small energy differences, since I remember that the tunneling is local in space, so you can jump only from one site to the next. So to reach a site which is at distance r, which depends on how small I want the energy differences to be, we'll have to act with this potential term at least a number of times, which is of the order of this distance r. So this means that my effective tunneling will be itself very small, typically. So it will be this small constant j to the power of the distance between these two sites. And so I have a continuous competition between how small I ask the energy difference to be and how far the sites effectively are, and therefore how small is the effective tunneling between these two sites. And what I have to show is that systematically, if I go larger and larger length scale, it is always the smallest of the tunneling that wins. So I systematically find, with probability 1, at larger and larger distances, that the energy difference becomes smaller and smaller, but my tunneling also becomes smaller and smaller, and the tunneling is smaller than the energy differences. And therefore, I keep being into this situation of having sites which are non-resonant. So this is the basic mechanism, and this is what one has to prove when arguing for this localization, and this is what we will translate into a calculation tomorrow. But somehow, if you then go back to this simple example, and I told you that typically it happens that these sites, even if you go further and further away, they keep being non-resonant, then you know that your eigenstate, if you just restrict to these two sites, will look like that. So you will find one eigenstate which is large on one site and the other one which is large on the first site. Now, of course, you cannot reduce to this two-level system, so you have to include all the other sites in your calculation. But if you do this, you find that the result is pretty similar. So you find that your eigenstate indeed are large only in some finite region of space. And if you go very far away, you have this exponentially small tail. And this exponential suppression comes from the fact that your exponentially small tunneling is winning in here, and it is giving you this, this decaying tail. And this also tells you something else. It tells you that in these localized systems, there are resonances. So you have to hybridize a bit your local degrees of freedom. So when you think in terms of perturbation theory of diagrammatics, I mean, you have to be careful when you want to distinguish convergence and not convergence. So there will be local regions where you do not converge. But those are only local, and they are typically confined in this typical length scale, which is the localization length. And if you go asymptotically far, you recover your convergence, and you see that you don't need to hybridize your degrees of freedom anymore. Okay, so I hope that this gives at least an idea of why you need the disorder to generate this. So it's really... Absolutely. So the question is, what happens if we change, if we do not have a hopping which is just strictly local in space, but if we allow for long-range hopping. And there things depend on how long-range you make it. So you can choose distribution of your hoppings which are power low. And then you will have critical powers which depend on the dimensionality. So you can reason in the way that we will discuss tomorrow, and you will find that indeed if you have a little bit of room of making your hopping less local and a bit more long-ranged, but there will be critical power in the distribution which depends on your dimensionality, and if you go beyond that, you destroy this localization. I hope that answers. So if you reason perturbatively, what you do is you yes. So yes, this is a broader question. So to what extent what I'm saying depend on the distribution of the disorder? So people, when doing, let's say in physics literature, usually they just choose one distribution of the disorder, let's say the bounded one, the box distribution, and they argue for that. But if you look at results in mathematics, you will see that there is an universality, a robustness with respect to the distribution of disorder. So you maybe have to impose some conditions on the fact that you need some moment that is bounded, but apart from that, you expect this to be robust. Okay.
Yeah, so is it correct to say that this is purely a wave phenomenon, and so that you could also have that in just with classical waves, or is there something that is really quantum about this?
No, you can have it with classical waves. Usually there, you want to be in low enough dimension.
And okay, so do you know examples of classical systems that have Anderson-like localization?
So there are experiments with waves. There are people in France. I can find the reference for you where they see localization of waves.
Okay, thanks.
But somehow, okay, so let's say if you just think about Anderson localization, there is an issue of dimensionality. So there is, first of all, there is a special dimension which is 2, such that if you go below 2, no matter how weak is your disorder, you do localize. But the way you understand localization in there is a bit peculiar, and it has to do with backscattering and destructive interference between paths. So one path and the time reversal of the path, for example, in 2D. And that is something that I think you can probe also with classical waves, and you see evidence of this. Now, if you go to higher dimension, then this way of thinking about it in terms of resonances and suppression of tunneling, I think it's more natural, to the point that this, you manage to extend it even at infinite dimensions, so on the Bethe lattice, for example, where you have no loops and you cannot argue about destructive interference of path and the time reversal version of the path. And when you reason in this way, I think that the fact that you have quantumness and that you have, let's say, discrete energy differences in your perturbation theory, it matters. It matters there. But in low dimension, you can think of this as being a wave phenomenon, and therefore you can extend it to situations where you're not quantum in principle, but you just have interference of classical waves. Okay. Okay, so now I will conclude the introduction. Yeah, I know, it was an introduction. By coming to this issue of why, let's say, as we said before, the sigma z operators in that particular case of the spin chain are a little bit special, and they allow you to probe ergodicity breaking at variance with the sigma x. And this has to do with integrability. So we discussed all of this phenomenology, no transport, violation of ETH, and role of disorder, and ergodicity breaking. And somehow I think it's very natural to ask how close are we to other class of systems where we know that convergence to thermal equilibrium doesn't happen, which are integrable systems without disorder. And in that case, we know why they do not thermalize. So we know that there are many symmetries, so many operators which are conserved. And these operators have a peculiar structure, so they are local in the sense that I specified before. And the fact that you have this many local conserved quantities really constrains your evolution, and it is what forbids the system to thermalize, at least to this Boltzmann-Gibbs measure, which depends only on temperature. So you may wonder whether something similar is going on in here, and this is a question which was raised, and I think around 2014 by people like Vadim Oganesian, David Hughes, Dima Banin, and collaborators. And indeed, what you can say, so I will state it as an expectation, and then I will tell you how much we know. So you can expect that also in this MBL system, you have such conserved quantities, so that there exists an extensive and complete set of operators that I call I alpha, where now I'm considering, for example, in 1D, so alpha goes from 1 to L. So these are operators that in the literature people call LIOMs, which simply stands for local integrals of motion. And they are such that they are conserved, so of course they commute with the Hamiltonian, and they are also independent, so they commute with each others. And moreover, they have two more features. So the first one has to do with what is the locality structure of these operators. And the word that is used in this MBL community, which is perhaps confusing for people doing integrability, but it is the word of quasi-locality. Where quasi-locality for me means that if I look at the norm of this operator on my lattice, I find that this norm looks exactly like an eigenstate of a single particle Anderson Hamiltonian. So it is exponentially localized. So if I have my lattice here, what I find is that if I plot, let's say, the infinite norm of this, one particular of this operator, I will find that this norm is large only in a finite region. There is a typical length scale again, which I call now psi many body or operator. around a specific point, which I call the localization center of this operator. And then down here, so away from this localization center, I have exponential tails. And this is a notion of locality which is very different with respect to the one that you have in Bethe sets like integrable systems. So in here, you see that you are almost strictly local in the sense described above, in the sense that if I now truncate my operator at this finite length scale, I will make an error, of course, because I am forgetting about this exponential tail, but this error is exponentially small. So what I mean is that I can approximate the norm of my operator up to exponentially small terms, and the truncation is conserved up to exponentially small terms. So it commutes with my Hamiltonian up to exponentially small corrections. It's almost a strictly local operator in here. And the second feature is that if you then, so the set is complete, so I can write the Hamiltonian as a functional of these operators. And what I find is that I have arbitrarily higher order interaction terms. So my many-body Hamiltonian, okay, there might be a term which sets the scale, which does not depend on these operators. But then I will have a sum of linear terms. I have pairwise interactions. And I can go on. So I have arbitrarily high or long strings of products of these operators, with a feature which is that the couplings in here, so H alpha beta 2, for example, these are themselves exponentially decaying. So the strength with which two operators, I alpha and I beta, interact is set by the distance between, for example, the corresponding localization centers of the operators in my lattice. So this will decay as e to the minus divided by some scale psi. And the same for higher order terms, where, of course, you can take here the maximal distance between any pair of the operators contributing to the product that you're looking at. Okay, you can ask another thing to these operators, which is that as your original degrees of freedom, in particular if you think about fermions or spins, they also have a binary spectrum. These are zero, so you can interpret them as occupation numbers if you think about particles, or sigma z or spin operators if you think about spin chains. Okay, and now the idea is that if you combine all these ingredients, so if you assume that this is true for your model, then you can really deduce, so all of these conditions allow you to, so this implies all of the features that we have discussed about many-body localization. So in particular, just to give an idea, so if by using this peculiar structure in space of these conserved quantities, you can plug them into your Kubo formula, and you will be able to deduce that, that you have no DC conductivity. So A implies no transport. Whereas you can argue that this particular structure of your Hamiltonian with such interactions which are exponentially decaying is anything you need to get out this logarithmically growing entanglement entropy. And this is an exercise if you want to look at this. But perhaps you can already get an intuition in the case of log t, so just to answer to the question. So this, to argue for the log t, it is enough, for example, to consider this coupling term in here, and then you know that, let's say you can relate this entanglement entropy to the number of degrees of freedom which have dephased up to time t. And now up to time t, you will have dephased, so let's say 2 degrees of freedom will dephase at a time which is roughly proportional to the inverse of the interaction coupling between them. So if the interaction coupling is exponential in the length, then you get that this you can relate to the time scale at which they dephase. So you have a relationship between time and length, which is time going like exponential of the length. So you have a length which goes like log of t. And then the amount of entanglement that you have at time t is scaling with the number of degrees of freedom that you have that have dephased. And this is roughly scaling extensively with this length, and this is how you get the log of t. So this was very sketchy, but I mean, if it is to say that the logarithm comes out because you have this exponential decay of the interactions between these degrees of freedom. Yes, exactly. This is?
I was saying that if the entanglement entropy grows logarithmically in time, one should expect that if you do a quench correlation function, they show a light cone which is logarithmically growing. I mean, yes. That would mean basically, yes, that inside this light cone nothing happened, or outside.
Yes, so when you say it has been checked, you mean numerically or you mean...
some way.
Analytically. No, you find numerics on logarithmic light cone. Okay, and you find somehow phenomenological argument which starts from here and use this as an effective model to then deduce time dependence of correlation functions.
So are you going to explain the log in more detail or not?
It's an exercise, but if you're interested, maybe next time I can do it. Or maybe later or in the discussion, because it takes a bit of... Yeah, okay, we are almost done.
So, I mean, okay, so usually when you have a log, the prefactor is interesting, related to some, maybe to some critical exponent or something. So does it have a meaning here, the prefactor of the log?
You mean the prefactor of the dynamical evolution, not of the saturation?
No, of the one you wrote here, S of t proportional to log t.
Yes. I don't know if we know if we can go beyond just the log t scaling.
If this comes out of a calculation, then the prefactor must be known, right? And what does it involve? Is it?
No, I mean this. You argue. So you start from this, and then you essentially truncate at this level, and then in that case you can write down an explicit form for the prefactor, but it is not an exact calculation. So the prefactor then will contain information on the particular initial state that you start from, and
It's complicated. It's not like one
I
half.
would
Or,
say so.
Okay.
Okay, so maybe I will just conclude by adding a comment. Yes. Yes, the point is that which length scale? I mean, the question is, from your argument, I imagine that the prefactor is proportional to the correlation length. It's true. Then, in principle, I mean, there is some debate on whether there is just one length scale or one psi or more than one psi. So there is one psi which appears in the interaction. There is one psi which appears and which controls the decay of this norm. So if you assume that this is the same, then yes, this will enter in the prefactor. But it is not obvious we have length scales which matters here. Okay, so the question is whether these length scales are very different. So that depends on where you are. So if you are close to the transition, things become difficult to check. Of course, if you are in the limit in which the disorder is very strong, no, I think they are pretty close. Okay, so do we have time for one comment? Yes, one comment. Okay. So, okay, the comment is I presented this as an expectation and as a framework which is unifying in the sense that it allows you to argue for all of the phenomenology that that discussed. Now, one first comment is that when you think about rigorous mathematical proofs of this MBL, this is the approach that you follow. So you do not look at conductivity as in the single particle case, but so there is one work basically, which is the work of John Imbrie, where he considers one particular spin chain with disorder, and he looks at the structure, at the local structure of the unitary operator, which diagonalizes the Hamiltonian, and he characterizes this, and from this result you can somehow deduce that, or this result implies that you then will have conserved quantities which have this quasi-local structure in space. So this is one comment.
Could you write rapidly the Hamiltonian considered by Imbrie, please?
Yes, so it's a random field leasing. So now you choose, let's say, okay. It's all random, all the couplings are random. Let me call it H I sigma X. And then you break the symmetry here by putting another H J tilde sigma Z.
Thank you.
And all these couplings are random variables. And this is what people call an almost proof, in the sense that there is an assumption that he needs to prove this, but provided that you believe that assumption, then all of this follows. And the second comment is, well, what do you do concretely if you now want to, if you start from one Hamiltonian in terms of fermions, for example, and you want to build construct explicitly these conserved quantities as a function of your fermionic degrees of freedom. And this is something that perhaps we will start with next time. But the idea is that you can think about working perturbatively. And you can do this because you know what are these local integrals of motion in the case in which you have no interactions. And this is the set of occupation numbers of your single particle eigenstates of your Anderson-Hamiltonian. And because your Anderson-Hamiltonian, so the Hamiltonian without interaction is Anderson localized, you have wave functions which are exponentially localized, and this implies that the norm of these occupation numbers has precisely this structuring here. This set is obviously complete, so you can write the Hamiltonian as a function of these operators. And the only difference is that in the non-interacting case, the function is simply linear, so you don't need to add higher order interactions. This is what, for example, gives you an entanglement which saturates and doesn't keep growing logarithmically. So the problem is solved when u equal to 0, and then what you do in the generic case in presence of interaction is to try to dress these occupation numbers. So you would want to write this I alpha as an alpha plus corrections which come from the fact that you have interactions, and this is very similar to this idea of Landau quasi-particles that you build when you do Fermi liquid theory, which was recalled by Sachdev, I think, last week, but with crucial differences. The first one is that now these operators is not that they have a parametrically large lifetime, so they are really conserved in this case, and also you don't have to restrict to the Fermi level. You do this construction at the operator level, and this will characterize the whole spectrum of your many-body Hamiltonian. Okay, so I think tomorrow I will maybe comment a bit more on this, and then we go to the calculation of, in the case of the Anderson model.